It's good. Actually, yes. Thanks overall. Thanks for reaching us out. I think that the first time we learned about your project is that probably you or someone else tweeted, and we just and that's interesting. I also wanna. I'm representing Apache Ignite community, one of the committers and PMC members, and for me, it was always interesting to understand like what exactly you guys here do.
Okay, well, that's
very
exciting.
And that's the place. I know that you have already conducted a webinar, but usually those webinars with Great Gain, they're for a mixed audience, like for people of different, let's say, occupations. But in here, we do expect only Ignite community members, like Ignite application developers and community members to come. Most of the guys should be application architects and developers and engineers. So that's the guys who would like to grasp and understand what exactly you built and how you use Ignite. What were the problems? Don't hesitate to talk about problems, because that's also the opportunity for us to learn what's bad with the project, how we can improve. You should have stumbled upon some of the issues, and don't hesitate to bring them up, because it's all fine. That's the right place to do it. Here is we have community members, we have users, etc.
Well, great. I really hope that you are also going to find our use cases interesting, and yeah, like it's really exciting. So thanks a lot for giving us this opportunity.
Yeah, and also what's interesting, speaking about the future of Ignite, just if I'm not mistaken, 5 days ago, we started a conversation finally about Ignite 3.0. Not a conversation, but we decided to move forward. So eventually we want to start working on that next major release, cleaning up the APIs, removing redundant code and introducing, more elegant and more user-friendly capabilities. So that discussion is already running, and we're also hoping not only to get everyone's perspective over the mailing list, but also we are planning to schedule an Ignite 3.0 conversation meetup in this group, so that you can come. Because for some people it's more easily just to come and share feedback by seeing each other and talking to each other.
Yeah, well, that's very good opportunity. I mean, we did a couple of extensions, like not of course on the code base. It's kind of like external extensions, but there are a couple of things that I can imagine that maybe if our use case is also shared among other users, that you might consider those approaches. So it's a very good opportunity.
We can start. It's 7:05 in my time zone.
Okay.
And we will have the video. So if someone will miss the very beginning, we can share the video and they can watch it. So hi all, thank you for joining us today. I'm Ksenia. You probably know me from by my emails in groups and on our mailing list. And today we are talking about using Apache Ignite for creating framework for blockchain network. That's one of the very interesting implementations of Ignite. And I pass a word to Branimir Angelov, who will share his experience about using Apache Ignite. As usual, all the questions our speaker will answer after the talk, but you can just type them in a chat, and we will get back to them after the talk.
Also, probably here is Ksenia, if you let me, just to step in for a minute.
Sure.
It's up to Branimir. Branimir, if you want to take questions and make pauses during your conversation, it's all fine. We can let you know, like when let's say you come to some logical ending in one section, you can check their questions, like the chat window, and you can answer them before the ending. So it's up to you. It's always up to you, whatever you prefer.
Well, okay, that would be very good. Actually, it's perfect for me because I have a lot of diagrams to really have questions during the slides. I'm really not sure if I will be able to really check check the questions from the chat window, but this is something that I have to figure out.
If something, I will read them for you, no problem.
Oh, can you do this? Wow, that's fantastic.
I'll monitor them, and if you have something interesting, I'll let you know.
If there's something interesting, absolutely, just interrupt me and let's discuss the question right on spot. Okay. Okay, very good. Thank you, Ksenia. And so let me now expand a bit the introduction that Ksenia provided. So I would like to explain you a bit more about 3 companies that are involved in the technologies that I'm going to talk about. So the first one is Kubo, which is a company specialized in creating private cloud solutions for European businesses, mostly using cloud-native technologies and Kubernetes. And actually, one of our customers is Vecto. We have provided first-party high-performance infrastructure with bare metal servers, GPUs, and directly attached network storage for one of their internal projects, which is a crypto asset algo trading platform that is collecting data from various marketplaces and doing online data processing as well as offline data processing, training machine learning models, and so on. So when we were discussing the infrastructure for those machine learning pipelines, actually we come with the idea to use Ignite for both online data processing and offline data processing, and really combine it with the serverless framework. And we created Perper, which is the first part of the presentation. Then we showed this framework to one of the Vecto sister companies, Comrade Cooperative, which is a democratic organization of software developers and innovation builders that are doing blockchain applications. So they have 2 key projects, like Autonomy is the first one and Apocryph is the blockchain. But the key project here is Autonomy, and when they were trying to implement the Autonomy project, I'm going to talk a bit more about it during the presentation, on the existing blockchain technologies. However, this was not so much successful because of the specific requirements of this project. So when we presented them with the Perper technology, they kind of liked it, and we start thinking about, okay, why don't we create a blockchain based on this technology and keep development experience. So yeah, this is how all started. And now, before going to the technical details, I would like to do a very quick introduction to reactive programming. Really not an introduction, but kind of a very high-level overview, because everything that I'm going to talk about is really only about reactive programming. Here I have created like a small computational graph that I would like to present you, and also kind of present you the notation that I'm going to use through the presentation. What's reactive programming? Reactive programming is pretty much programming with asynchronous streams. So what we have is entirely data flow driven computation. So here, imagine that we have some sort of a consumer that needs to consume data from a processor, that needs to get the data that is processing from some sort of a generator, and actually is getting the data from 2 generators. One of the generators is harvesting some sort of a file system, or like a cloud-based file storage, and the other one is consuming some sort of a cloud service. Then when the data is generated, it's propagated back to the processor that is doing some processing, and it's propagating it back to the consumer. The interesting thing about the computational graph is that you can add another streaming section, so another subgraph inside it. So we can have another consumer that is having another processor that it can engage the same generator that the first stream has already engaged. And then the newly generated data is going to be also propagated to the new processor and then to the new consumer. Of course, we have to have the ability to somehow query for all data as well. This is pretty much the idea, like a very high level idea of reactive programming. And it's very important that the reactive systems, which are following the reactive programming ideas, they have to be resilient to failure, elastic, message driven, and fully responsive. And in essence, actually the data processing pipelines and the blockchains, they share the same characteristics of the is defined in the Reactive Manifesto for our reactive systems. Another thing is that what we're really interested in is in distributed reactive streams, which is reactive streams. It's kind of a term for asynchronous streams with non-blocking back pressure. It's something that is quite well adopted even in the modern languages like Java and C#. But what we are really interested in is into the distributed aspect of reactive streams, really the ability to have the streams distributed as distributed systems, so they are really resilient and highly scalable. Another thing that we are going to talk about a lot in the presentation is about serverless computing. So here is really about having the ability to run computation without really managing the underlying computational resources. And of course, because you're probably familiar with all of the technologies like Azure Functions, AWS Lambda, and so on, they are really stateless. So you have to have some sort of external state management capability. And last but not least, it's a really important aspect is the ability to configure data locality. So what we mean by data locality? I mean, since you have to do some sort of state management, for example, we can have processors that are aggregating some sort of a data coming from a generator, and when doing the aggregation, they are building a large data set. It's very important to make sure that the computation related with aggregation is collocated with the data set that the processor is building. Similar thing can apply with a processor that is actually processing a very large data set that comes from a generator. Then we would like to make sure that the processing logic or the workers that are doing the actual processing are collocated with the data set that is generated by the input stream. So configurable data locality, this is something that we are kind of adding as additional concern when we would like to build a reactive programming-based environment or a platform. And it's something that is very important, especially for machine learning pipelines, ETL tests, and others. So now let's talk a bit more about why using Apache Ignite for building this kind of platform. So the main 5 arguments. I mean, we were investigating other platforms, so it was not a kind of an easy decision. But there are really 5 top arguments about Ignite that we really liked about, and we decided to really base the whole infrastructure on it. So the first one is what we call a Swiss Army knife argument. So the idea is that the Ignite as a platform it's a highly configurable, it's a very lean platform, and you really get the necessary features, really the 80-20 rule, the necessary features to create a reactive programming framework. And usually, in order to achieve this with other platforms, you have to combine several of them. So the second one is really the in-memory computation model. So when you do a message-driven system, blockchain is such kind of system. It's really important to make sure that you have a super fast computational model, memory-based, so you can have a high throughput. The third thing is around persistence. So we're really using a serverless environment for the actual computations, and it's very important when you have a dynamic computational graph and when you have a dynamic environment of scaling up and down the actual computation to be able to have a solid persistence, so you can query for historical events and to be fully resilient to failure. The fourth one is easy for integration. So Apache Ignite can be run in process in various environments. Specifically, we're using it from C# and .NET Core, and also we are using the thin clients from Python and C#. So for us, it was really important to have a very good multi-language support. And the fourth argument is the advanced clustering capabilities of Ignite. So you have a full transparency by using Ignite. You have a full transparency over the cluster behavior, so you can configure things like data locality and in various ways. So these are in a nutshell the main benefits of using Apache Ignite here. And now let's see what exactly we have built and how we have built it. So we have those layers. As a baseline, we have a standard Ignite cluster. Then we are using Ignite cache. to store the computational graph. That this is pretty much the metadata information about all the streams, the way that they're connected to each other. Then we have an orchestration layer that is based on the changes in this computational graph, is orchestrating the actual computation. Then we have another cache layer that is responsible for storing and buffering the actual stream of outputs. Then we have another service layer of responsible for the actual execution of the streams and their logic. And on top of it, we have another service layer with responsible with the transport and pretty much offloading the actual computation to the serverless environment. So this serverless environment, we call it Perper functions, and it's based on Azure functions. But here it's very important to know that by Azure functions, we don't mean the platform as a service feature of Azure Cloud. What we are referring to as Azure functions is actually the open source Azure Functions Runtime, which is a .NET Core technology for running serverless workloads that you can host in any cloud provider by using Kubernetes. And this is actually what we are using as well. Okay. So now I'm going to present several interesting implementation details that we have created while trying to implement Perper. So the first one is how we have implemented the data locality. So what we're going to now focus is really on the lower part of the diagram from the previous slide. And what we have here is we're just having like two nodes. And we're just going to show you how the updates in the caches are propagated to the actual stream managers who are responsible for the execution of the stream logic in a way that it preserves data locality. So now we're going to let's just focus on two major data locality configurations. Like the first one is going to be a data locality that is bounded to the input of the stream. So imagine kind of a generator that generates a 2 GB data set. And you want to have a consumer or a processor that is listening for this stream. And every stream item is a 2 GB data set. So we want to make sure that any sort of processing that you're doing is going to be collocated with the data generated by the generator. So in this case, what we are doing really is we have the stream orchestrator, which is a cluster singleton service that is observing for changes in the streaming graph. And when a stream that has this data locality configuration that I have mentioned is created, then what we have here is a proper configuration of the continuous query to make sure that the propagation of the change to the services layer is going to preserve data locality. So what we do here, so we're using remote filters to make sure that when the cache event is generated, so when the new data set is generated and added to the cache, to the cache of the stream, then on the event, on the node that hosts the event, basically on the same node, we're propagating the change and we are doing communication to the actual service. So the stream management services, as you can see from the previous diagram, they're cluster node singletons. So you have one of them for every node. When the change is propagated to the stream manager here, we make sure that the stream manager that is activated is the one that is collocated with the actual data set, and the computation can continue from them to the serverless workload. Another scenario is exactly the opposite one. You have a generator that generates a number of very small messages, and then you have some sort of aggregator or processor that is doing aggregation and putting them in a large data set. In this scenario, most probably you're going to have a state that is used for the aggregation, and you might want to make sure that the serverless computation is done and it's collocated with your state, which is pretty much collocated with your stream descriptor. So in this scenario, what we have is that the remote filter is passing the event back to the continuous query, and then the continuous query is using affinity call to locate the actual stream stream manager for the specific stream ID. So why we are using here Affinity code? The reason is because we cannot guarantee where the stream orchestrator is going to be located. We also cannot guarantee whether the event is going to originate on a node that on the exact same node that has the stream manager for the particular stream. So this is why here we have to do Affinity code in order to locate it. Another very important thing here actually is that in order to minimize the network load, the load on the network when we are using those remote events, we can really use here remote transformers. It's a new feature in Apache Ignite 2.8. Unfortunately, it's not yet available for .NET, but it's something that we're going to use it as soon as it's available. But it's a very important optimization that we have to make sure that we do. Like for example, here it's not necessary to transmit the full event to the stream orchestrator. You just need the keys to make sure to be able to configure the Affinity code in the proper way. So now the second interesting aspect in terms of implementation of Perper is scaling in back pressure. As I mentioned, non-blocking back pressure is an essential feature for the reactive streams. So how do we implement those two? As I mentioned, we're entirely using Kubernetes for all of the operations of Perper, and all of the Azure functions that are contained in actual computations are implemented as Kubernetes pods with Azure Function Runtime and extension that includes the Ignite client. This basically means that every stream has attached computation that is a particular pod which can be scaled up and down and managed as a Kubernetes deployment depending on the workload that is handled by the pod. So this gives us a very flexible way to really scale the system to scale the computation part of the system independently from the data part of the system. So the second thing is what we do about the back pressure and actually how do we manage the whole computation. So let's now imagine just the high-level computation flow. So we have a generator that generates kind of a data set, and then with the thin client, this data set is written into the stream caches, and then the changes that are happening into the cache are propagated to the stream manager and then to transport. And based on the configuration of the streaming graph, a particular worker or processor are being notified for the changes, so they can obtain the new information from the cache, do some processing, and then save the results back into the cache, which again is doing another propagation to the transport layer, and so on and so on. So as you can see, the whole computation is happening. The computation is happening through the Ignite data node. So there is no direct connection between the stream computation units. This basically means that we now have a very high-level, universal, natural strategy for flow control and back pressure. We can basically buffer in Ignite all of the information while the system is balancing in terms of scaling for the actual workloads. So now let's examine a bit closely what is happening in terms of flow control. So it's very important that although we are using Ignite caches, this propagation of the events to the actual function pods is happening in memory. So we have to make sure that we're not overflowing any memory buffer. So this is why what we're doing is that when we have a continuous queues here, all of the propagation between the services is happening through bounded channels. You can think of the bound channels as it's .NET Core feature, but you have it from in many other languages. It's a kind of an in-memory queue used for kind of producer-consumer type of function of communication between threads. So then we have basically a reverse socket that is connecting the actual function pods with the Ignite node, and the transport service is propagating notifications to the function pods. Here it's very important that we should also have some mechanism for back pressure and flow control to make sure that if the notifications are processed slowly, there is not going to be any memory overflow. And luckily, what we have here in the system I/O pipelines as part of the .NET Core, we have such kind of a back pressure configurations and mechanisms that we can use to really buffer into a near cache any notifications that are not yet processed, that we are not able to process in the function pods. And when the function pods are scaled accordingly, the transport layer can send the notifications back to the function pods. Of course, here we can have some strategies for dropping out notifications or patching them together. So what else I would like to? Yeah, so this is pretty much the scaling and back pressure. So now let's think about how do we operate the whole solution. Oh, okay. Actually, there is one important aspect that I would like to mention. So it's again a very cool Ignite feature that's added in the latest version. So we have partition awareness in the thin client, and this is quite important, especially when we are recovering from certain events in the cluster, like for example rebalancing the pods or having a physical node that is turned off and redeployed to another one. We are able to actually to make sure that the system is still having a decent performance because of the ability for thin clients to connect to the right node. And also it's quite important when we have in the case when we have data locality to the state of the stream, because in those cases the notification that are received by the stream processors, by the actual stream functions, are going to contain keys for objects that are located into a different Ignite node. And then here the thin client and the partition awareness of the thin client make sure that we're not going to do any additional network round trips between the actual Ignite nodes. So in terms of operations, what we are, as I pointed out, we are entirely using Kubernetes. And the good thing about Azure Functions is that it's natively integrated with KEDA, which is a Kubernetes event-driven autoscaler. It's a Kubernetes operator for doing autoscaling. It's quite well adopted with a great community, and you can easily extend it. So how do we use this and how do we extend it? The way that we do the deployment in order to maintain the data locality is that we want to make sure that for every Ignite node and function application, we have one deployment object that is managing the function application, which means that for every Ignite node and application, we have a deployment object. We have a separate deployment object, and the KEDA autoscaler is basically scaling and controlling this deployment object. How we do this? For this deployment object, we have a dedicated external scaler, which is part of the Kubernetes operator. And then we host a small gRPC server as part of the Ignite node, as part of the transport layer, that is broadcasting the metrics to the external scaler. So basically, any information here about the flow control, we are broadcasting it to the external scaler, and we are making sure that based on this information, the pods here are scaled up and down. When we are deploying the actual pods, and the configuration of the deployment object is that we should there is an interpod affinity between the Ignite pod and the pods containing the actual function to make sure that the data locality is also maintained on a physical level. On the Ignite side of the things, so managing the actual Ignite nodes, we're doing a very straightforward deployment of Ignite in Kubernetes with stateful deployments. The only specific thing is that we have here interpod anti-affinity to make sure that the actual pods are well balanced through the Kubernetes physical nodes, and each of the physical nodes has directly attached storage. Okay. So this part of the solution, the whole configuration of around the external scaler, is not yet available in GitHub, but it's something that you can, like if you start the repo and stay tuned for our updates, it's something that we're going to push in the next month. So now I would like to show you kind of a short demo. Like if there are any questions, I think it's a good time to answer them at this stage, because I'm showing a demo and then moving to the blockchain part.
Branimir, I see one question. Have you compared to some other ETL tools, for example, Apache Ignite?
Actually, well, with this particular, we haven't done a detailed comparison. We were mostly focused on Spark. So this was our first choice when we started the project 2.5 years ago, 2 years ago actually. Yeah, for this specific one, we haven't done any comparison. But with Apache Spark, the main advantage here that we have is really the development model, that we are able to really use Azure functions, which are very well equipped environment in terms of development for both Python and C#, and also the ability to have online data processing. So kind of the ETL is only part of the things that we do in Vector. As I mentioned, the system that we wanted to create is both for online and offline data processing. And what we were thinking about is that like if we have a good framework for doing the online data processing, we can easily adapt it for offline. However, the other direction is not so easy.
Okay, thanks, Alexander. Did we answer the question?
Just in case, Alexander, if you want to unmute, that's the right time to do that. You can talk out more details with Branimir if you want to. While we are waiting, I also wrote down several questions on paper.
Okay.
So you kind of, on your first slides, you showed that you selected Ignite services APIs for your stream managers and other components. And the question is, how do you update those services? Do you use any rolling upgrade procedure? How do you do this to ensure that there is no any downtime? Or do you imply any short downtime?
Yeah, so in terms of, okay, so the question is like on two levels. So the first one is a very important clarification. Those services, they're actually quite abstract. So they're part of what we call Perper fabric. And the actual computation is offloaded to the Azure functions layer, to the serverless layer. So the actual Ignite services, they contain really a system logic there, like really like an abstract computation control logic. So we don't update them very often. So when we're rolling out a new update of the actual application, we're usually just updating the serverless environment. All of the data is and the way that we deal with data in the fabric side of the thing, so like on the Ignite node, is entirely in the binary mode. So we are not referring any end user classes for things like this. However, still we have to, at some point of time, update the runtime, and this is what we do with the rolling updates. But this is happening it's very rare.
Okay. And also you mentioned that you heavily utilize Spark. Where do you run Spark? Do you run Spark on these function pod nodes? Do you use it for the processing of their events, for the notifications, or do you also use it for the generator? How does it look like?
Okay, I'm sorry, Dennis, maybe I have somehow kind of misexplained this. So what I mentioned is that we were considering Spark in the beginning as an alternative approach. But now with this solution, we are not using Spark at all. What we do is that the ETL part of the tasks, we're doing it by because of the functions, they have external state management. You can define kind of you can use them as a durable function. So you can define like a multi-step processes. and that also have state attached to each of the steps. So you really can achieve, and you can create the ETL kind of processing by just using Azure functions and the Ignite part of it. And this is what we do. Can like you have these regular batch jobs, and they're implemented only on purely on Azure functions and Ignite.
Yeah, and actually, thanks for clarifying that this Azure functions feature, in fact, is not somehow bounded to this commercial offering of Microsoft, because that was quite a revelation for me. For me, like Azure functions were always associated that I need to go to Microsoft and buy. Actually, I tried to run several like pet projects using Azure functions. I definitely will check those out, because that sounds interesting. And and is it correct? Is it correct to say that I can even run those functions on AWS or Google Compute Engine if I want? Yep.
Yep, absolutely. You just need to set up the. I mean, you just need to use their Kubernetes offerings, like for example, Amazon Kubernetes services or Google GKS, Google Kubernetes service. So you need to have Kubernetes environments where you can run them. Probably you can run them using Dockers. This is also possible. However, it can be very hard to manage.
All right. Thanks.
Yeah, the naming,
I'm done with my questions.
The naming is not. It's very confusing, but this is why they. I don't know why they do it that way.
Okay, so let's move to them. If Alexander will have some questions about that, he will, I think, type them in chat.
Okay, so let me quickly change the screen. So it's a very, very short demo, but it's going to kind of slowly. Do you see the source code? Okay, I hope.
Yes.
So.
Yes,
okay,
I do.
Thank you, Ksenia. So the demo is really like a very small multi-agent application that is kind of having two agents that are playing ping pong with each other. I mean, we're kind of now moving away a bit from this data processing, big data, ETL topics, and now we would like to focus more on the we can say it like the virtual actor aspect of using Perper, like really creating an agents that have some state and try to communicate with each other, because this is actually what is happening in a blockchain application typically. So what we have now here is we have those two agents that are streamed with associated state, and they're playing some sort of a ping pong with each other. The way that the application is structured is it's structured in a very modular way. So this is something that we have as part of Perper. We call it Perper structure. It's a really way to break down your application into multiple modules that can scale separately, and each of the modules contains a number of streams or workers. So here we have a kind of an application entry point or kind of main environment that is setting up the two agents. So here you can see like the source code, like it's a C#. So this is what we use. It's C#8, and we try to really create a very idiomatic experience, kind of very native to the latest development of the languages, developments of the language. So here we have created the ping agent. Then here we create the pong agent, and here we are kind of introducing the input of the output of the pong to the input of ping and vice versa. And here we have a very simple environment monitor that is just going to print the logic. So let me now try to start it. So now I'm going to start the actual Docker container that contains the Ignite node and the C# logic of Perper Fabric, which is the stream orchestration logic. And here you can see that in addition to the standard Ignite port, we also have this 4040, which is the port that we use for our custom transport of notifications and integration with the serverless environment. So, okay, so now let's see if I can move these around a bit here. Okay, so now we're going to start the agent. So as I mentioned, each of the agents is a separate application, kind of separate module. And here we start the main environment. So now what's actually happening is that the environment is connecting to the cluster, and then we start doing this ping pong. So there is a delay that I have added to the messages in order to make it more easy for comprehension. Otherwise, it would be like I'm just going to burn my CPU. So now I'm going to, like, you can see the agents are playing ping pong. So now I'm going to examine a bit more the code to really see what I mean here by just let me stop these two. Okay. Okay. So let's examine the agent ping. So as you can see here, what we have it's a very straightforward, very concise implementation. So we're using the async numberable, which is the reactive stream abstraction in C#. As you can see also here, there are no dependencies to Ignite. Everything is done into the Azure runtime extension that we have created. So the experience is really idiomatic experience, and all the interactions with Ignite you are doing through attributes. Here we are kind of sending the ping message. Then we are basically waiting for response from the other agent. Here you can see that the agents are entirely loosely coupled. And when we receive a response, we basically print it and then send back ping. Actually, and here is the delay that I have added just to make things more comprehensive. And here we also have the Pong agent. That is a bit more interesting because I'm also here showcasing how you can use the state attached to the stream. So for every message, there is an execution of this body here. So basically, notification is sent to the function pod that is containing the agent Pong function. So here you can see that this is executed, and we have a state that is attached to the actual function, and the state is updated on every interaction between the agents, and also the state is saved in Ignite as well. So, like for example, if the function gets relocated, or if you have, for example, several functions running on different Ignite nodes, and they're being notified in a certain order, they can share state by using, again, Ignite, using this state object here. So, like, pretty much this is what we kind of showed to our colleagues in Comrade that were building those blockchain use cases and the blockchain applications, and they kind of really like the development model, the way that you do development. And we start thinking about, okay, why don't we just add a consensus here on top of this and pretty much build the blockchain with those characteristics and yeah, see how it goes. So yeah, this is what we decided to do, and now I'm going to go back and explain a bit more about do a step back and explain more about the use case that we were building in Comrade, and really what were our concerns, and actually how we ended up of so much liking yeah, this development model. Okay, so let me now go back to the slides. Okay. So now let's take a part of the presentation about building really blockchain for autonomous agents. So by autonomous agents, what I mean is really exactly what you have seen in the code demo, like a small a small proactive agents that receive some sort of an input and and act on it based on their state and produce smaller output. So now, as I mentioned, let's do a quick step back, and really, I would like to mention more about the primary use case, the primary project that we built that we wanted to build and we are currently building in Comrade. So it is called Autonomy, and it's a technology, it's a blockchain-based technology for creating autonomous organizations. So what is autonomous organization? It's kind of a it's an organization that is not so much controlled by a specific people following a specific rules, by subjectively following specific rules, but it's actually an organization that is completely autonomous in terms of decision making, and it can proactively make certain decisions and basically do a self-governance. So the way that you can think a bit, it's a bit dystopian way of thinking, but you can think of it like when you're thinking about joining a new software development company, like instead of thinking about, okay, what type of person is my team lead, how he's following the work rules, what are the internal politics inside the organization, how can I get promotion and so on. What you can do is that you can go to GitHub, check out the source code that is containing all the rules in the organization, and you can audit those rules, and like if you like them, you can just go and work with the organization, because there is some sort of an environment that is making sure that those rules that are stored, for example, in GitHub, are operated in a decentralized way, completely autonomously and completely securely. So you can be sure that what you have written in GitHub is actually operated and is really managing the company where you work. So yeah, this is like very briefly the main mission of Comrade and this project Autonomy, and this is the main driver for us creating blockchain technology. So what are the requirements that, so maybe there is a one small clarification, maybe why blockchain for such kind of technology. So the reason why we want to have a blockchain is to make sure that the rules that I have mentioned that you can read in GitHub, they're executed by a completely autonomous and completely independent environment that cannot be controlled by a single entity or person. And essentially, this is the blockchain technology. This is the promise of the blockchain technology, and this is why what we are thinking about is that such kind of autonomous organizations typically and most logically they should live and be operated or they should run inside the blockchain network. So what are the requirements of such kind of blockchain network? So the first one is that we need to have free user transactions. So it's very important that although the organization is autonomous, there are members who are working as part of the organization, so they have to interact with it. So there are a lot of things that have to be voted, and in order to make sure that there is equal principle of inclusion of all people in the members of the organization, we have to have free user transactions, because for example, each vote is a user transaction in a sense. Then we need a high transaction speed, because many things are happening in the organization, and we need to make sure that we can reach consensus almost in real time. For example, if you want to figure out whether you should use this kind of technology or other kinds of technology, you would like to be able to complete this discussion in a relative real time. Then we have to be able to accommodate complex logic. So it's not just about some financial transactions, but usually the rules in organizations are quite complicated. Then we have to have easy to read contracts. It's very important that the way that you express those rules in source code is very concise. You have to express them in a very concise way. So like if you want to read it in GitHub, to be able to comprehend it quite quickly and objectively. And the last thing is the ability to have proactive agents, because there are things happening in the organization that are driven entirely by the organization itself. So yeah. So we have those requirements, and we try to use existing blockchain technology. So kind of a year and a half ago, we started with Ethereum. And the challenge that, I mean, you can check out the source code of in the GitHub repo of Comrade for each of the experiments that we did. and each of the failed attempts, all the source code is there. So it was a very promising beginning. Like we really start using this DAO framework based on Ethereum called Aragon, that is kind of adapting Ethereum to really be more suitable for creating such kinds of organizations. However, there are 4 major blockers that prevent us to deliver anything functional in terms of our own requirements. And the first one is that it's really hard for to make transactions, free transactions in Ethereum. Like usually the end users must pay for transactions. And then we have the performance issues. Like a typical transaction in Ethereum might take between 15 seconds to 5 minutes. And it's really hard to predict, and also the costs are volatile. And it's really hard to handle large transactions. There are many like very complicated transactions. In order to make sure that they are processed by the network, you have to stay within certain gas limits. And usually, what you do, you break your smart contracts and many other smart contracts to work around that. But this is making the whole code very complicated and hard to read. Yeah, this leads to the last item, that all of the workarounds that you and all the abstraction layers that you have to add, and technical and the specific techniques are making the contracts quite complicated, especially if they're modeling a complex organizational process. And yeah, I mean, actually, Aragon as a project, they have recently started thinking about also building their own blockchain in order to deliver the framework that they promised to their users. So then we moved to the next generation of blockchain using the Tendermint consensus and Cosmos. This was much better, I would say. However, we also kind of had a couple of challenges. So in general, the specific and the new generation of blockchains, they're quite young projects by themselves. They cannot compare to the huge community and history of Ethereum. So it's quite difficult to extend them and use them as a platform. There are a lot of missing documentation. There are some scalability concerns that we have about using Tendermint, because there are a lot of options of configuring the actual scalability of the network that you would like to achieve. But again, this is something that it's very hard to assemble. There is no kind of out-of-the-box approach. And also, it's very hard to predict what will be the end scalability of the system. There were also no proactive agents, but more or less we were able to kind of start extending Tendermint. We created this framework, Strong Force, which was a C# smart contract framework on top of Tendermint. But the problem was that we kind of have this kind of a young technology, and we are doing extensions on top of it. So it was really really difficult to manage. Yeah, in a sense, this is actually our very early version of Upgrade. So what actually happened is that roughly around this point of time, when we were trying to really make the Strong Force framework working for Witomi and implement Witomi on top of it, we kind of saw the developments in Ubectu, the sister company, and saw the demos around Perper, and we started thinking about, okay, that's a very good development model. Let's try to bring this development model further and really have the blockchain that implements all of our specific requirements, rather than trying to to assemble something that might not work. So what are the benefits of using Perper for building blockchain? So the first benefit is obviously that, as I also have shown in the demo, it's very easy to create a state machine using Perper. So it's very easy to create an abstract computational model based on state machine, and this is the fundamental thing about being able to implement independently verifiable programs is what is required for blockchains. And then we have the reactive paradigm. So we have, as I mentioned, blockchains, they can be seen as a reactive systems, kind of message-driven systems. And the good thing about Perper is that it implements the reactive paradigm in a very pragmatic and software engineering-driven way. So you have a high level language like C#. You don't have to deal with a lot of complexities of lower level languages like C++ and Erlang. So what we thought about is that by using Perper, we will be able to very quickly start really implementing the specific blockchain aspects and really leave the commodity and standard like operations, monitoring, scalability, and performance aspects to the underlying layers like Apache Ignite and .NET Core. Then we move to the pragmatic architecture. So what we decided to do in Perper is a very pragmatic approach. So we're using a kind of like technologies like Kubernetes and Apache Ignite, which are providing all of the large community and we have stability. And the last thing is that with Perper we can have a single platform that scales from testing to production without any major code changes. So basically you can have a single architecture, single code base, and you can scale it on a number of servers to create simulations, to validate your security and performance assumptions of the blockchain network, and also have the same code running on the actual community powered machines. So what's the kind of a very high level architectural overview of a blockchain? So we have every Apache blockchain actually it contains multiple multi-agent applications, and each application is running on its own dedicated chain. So this actually allows us to have a very good scalability and a very high throughput, because every kind of application is running on a separate chain. Then we have the blocks. Pretty much every block is referencing to a specific agent source code, and the parameters of the state machine, references between the actual agents, which are using the object scalability security model. And then we have the actual multi-agent applications. So the multi-agent applications, the agents can interact between each other, but also the agents can interact across separate applications. And this actually leads to also a connection between the chains. And then we have a dedicated set of virtual nodes, which are maintaining consensus for the specific multi-agent application. So for every chain, we have a single multi-agent application that's running on it with a dedicated number of virtual nodes. So now let's examine a bit more about what's happening inside a single blockchain, on a single chain. So here we have a number of virtual nodes, and every virtual node, it runs the following streaming graph. So it starts with a consensus, which is the core of the actual system. So what is happening here is that based on a specific algorithm, a subset of the virtual nodes, several virtual nodes, are selected to be proposals. So basically they propose the next block depending on the information that they have. And then here we run a snowball algorithm, which is a specific like consensus algorithm for determining for reaching a consensus for a single actual block proposal. So this kind of algorithm, it involves a queuing mechanism where every node is doing a query across their peers and asking them about what they think about the next block and the proposal that should be. And after a certain number of rounds, this consensus converges, and there is a single block proposal that is outputted by this stream. Then this block proposal is being validated by each of the virtual nodes. In order for this process to happen in a kind of a more performant way, the validator is also observing the queuing that is happening between the virtual nodes, and is maintaining a priority queue for actually validating the blocks. So when we have the converged proposal, like a single proposal, which is what we call a committed proposal, then there is a validator which validates the transaction inside the block, and we have a confirmed block. And then basically we're ready to start the next round. Then this confirmed block is broadcasted through an inter-blockchain communication, which by using gossiping is kind of like an epidemic-based protocol, which is propagating the confirmed block across the network, and not only across the virtual nodes in the actual chain, but most importantly across the virtual nodes of other chains. So basically, when you figure out that there is a gossip for a confirmed block that is relevant for you, like from a virtual node perspective, this block is again validated, and if it's valid, it's considered as a confirmed block and can be used for as a input for the next block proposal. And this is actually how the communication between separate multi-agent applications is being implemented. So now, at this point of time, what we have, it's a kind of a centralized system that has some virtual nodes that are actually independent from each other and can reach consensus on certain arguments or facts, which are the blocks. However, this is still a centralized system. So the question now is, how do we make this decentralized? Like, the centralized system is very good for testing and for validating the security and consensus assumptions that we have in the protocol that we have implemented. However, in terms of creating a real blockchain, we want to make sure that that we have a decentralized network and the different physical nodes can discover each other. And for that purpose, what we are using is IPFS. So maybe just let me do a quick step back. So now we have the virtual nodes, and we have a single network node, which is a single Apache Ignite cluster or single Perper cluster, which can span across multiple physical nodes, but is still a single Kubernetes cluster. So every network node in Apache is a single Kubernetes cluster. So we have other network nodes, and every network node it contains multiple chains with multiple validators. And a single chain, actually, the virtual nodes of a single chain, they can span across multiple network nodes. So it's not necessary to have and obviously it's very important to not have the full set of virtual nodes of a single chain inside a single network node. So the question now is how those Kubernetes clusters are discovering each other. And this is something that actually IPFS is a technology that can do a very good job around. It has a very good peering discovery. It has a decentralized pub-sub mechanism, maintains peering lists, and can be used for storage, for decentralized storage. So those blocks, and it can be stored also in IPFS. So there is a very convenient way that, together with the gossiping and the block stored in IPFS, for a new cluster when it's spinned off or joined the network, it can actually catch up with actually what's going on the blockchain. So how we have implemented the integration with IPFS? So this is the good thing about actually using Kubernetes and Apache Ignite, is that it's very easy actually to do those kind of integrations, because you don't have like a huge proprietary, not proprietary, but custom, like a custom C++ code. You kind of have a very well broad community with a lot of integration options, so you can really easily run IPFS as part of inside the Kubernetes cluster. And for every network node, we run an IPFS node. So basically, for every Perper cluster, in addition to the curing and gossiping streams that are propagating the information across inside the virtual nodes running inside this network node, we are also having separate streams that are observing for changes, and they're propagating them to IPFS. And also, if there are changes in IPFS, they're ingested through listeners inside here. So it's very important here that because of using Ignite, we're able to really keep all of the required messages and state of the blockchain network required by the virtual nodes inside the Ignite cluster. So the actual virtual nodes, they can interact only with the Ignite cluster, and we have dedicated streams that are just bridging out between the Ignite cluster and IPFS. And now the question is, how do we make this whole thing like like a trustless, secure, decentralized network. So the biggest problem of decentralized networks are actually two types of attacks. Like the first one is the cold start and the CBO attack. So the idea here is that most of the reputation networks, like the blockchain, they're very vulnerable. And in our case, in case of Apocryph, really the tricky point is how do we select the virtual nodes. So the good thing is that the proof of work networks are already providing a solution for those two types of attacks. And this is what we actually decided, is that we just isolated the aspect of our system that is vulnerable for those two types of attacks, and we just simply employed the proof of work inspired algorithm to actually solve those. So what's really here the idea? The idea is that we should be able to have a mechanism for selecting virtual nodes that is making sure that the nodes are going to be distributed in a uniform, almost uniform way across the network. And this is the first thing. And by this distribution, the idea is to try to minimize the number of malicious nodes in the network, because it's like the whole point here is that our consensus algorithm, it provides, like for example, it provides security and integrity only if you have a certain number of honest nodes. If majority of the nodes are malicious nodes, then the network actually is not secured, or it's stalled. So this is really the key here. How do we select the virtual nodes? And how do we select it in a way that we minimize the number of malicious nodes? And here is the proof of work aspect that we are integrating. So basically, for each chain, when a new multi-agent application is deployed, there is like a special stream graph factory stream. So it's a stream that is creating that acts as a factory of other stream graphs. So basically, this stream is interacting with another stream that is called miner, and this stream basically it's interacting with the component that is doing a small proof of work based on actually mining cryptographic keys with a certain prefix. And this algorithm is something that is called King of the Hill, and we have used it from one of the very interesting new blockchain projects called Automaton. So the idea here is that this small proof of work, the first thing is that it helps us to kind of improve and solve those two problems with the cold start and CBO attack. And but maybe just to mention the CBO attack, the idea here is that you have like if you have an attacker that can create a large number of pseudonyms and kind of behind those pseudonyms to control a big part of the network, actually it can compromise the characteristics of the network. So the idea is that with those algorithms, we are kind of solving those two problems. And the good thing is that we can also use the mined keys for cryptographic purposes in the communication. So for example, when the communication is happening inside the Ignite cluster here, there is no need for any specific cryptography. However, when the actual blocks or messages leave the cluster in the IPFS layer, or when from the IPFS layer they are ingesting the cluster, here is where you have to apply some additional cryptography in order to figure out the identity of the different peers and who stay behind certain identifiers or pseudonyms. So here, on the top of the King of the Hill algorithm, which is providing a very, very good foundation, where we have to extend it a bit, because what is guaranteed by the King of the Hill is that from a historical perspective, the network is the network has certain characteristics. However, what we want to make sure is that, for example, like if you have certain nodes elected by using this sort of mining, so you're sure that as the mining goes, the nodes are most probably honest, and there are a sufficient number of honest nodes. However, you cannot know what will be the behavior of the node after it mines a certain number of keys. Like it might change to a Byzantine node. And this is why we are adding a salting on top of the king of the hill mining. That's what is trying to do. It's really trying to add additional layer of randomness and temporality in terms of time in the election of the virtual nodes. So what is really happening here is that when a certain keys are mined, they're being gossiped. They're being gossiped through the network, but also when the actual block gossip is which is related with the new blocks related in the chain, this new gossip is also being processed and filtered, and based on those new blocks, basically we have a kind of a time independent way to actually reset the salts or randomize the salts and propagate them back to the chains, which propagate them to the miner, and basically have a new way of determining the actual virtual nodes. So pretty much with those aspects, we have kind of created a consensus network for autonomous agents that have the following features. Like it's very optimized for developer activity, like the use of high-level languages. It has proactive entities, so we have a native features of scheduling reminders that can remind a certain agent to activate and produce a certain functionality. We have free user transactions, so basically the agents, they can pay on behalf of the users for certain transactions. We have the scalable network and nodes thanks to the Apache Ignite and Kubernetes. We have interoperability and extensibility, kind of natively implemented in the network, and also we have this serverless consensus that I mentioned about. So yeah, this is pretty much the blockchain part of the discussion. So I'm sorry for going a bit over time. So now it's time to answer some questions. Maybe I will, while we are thinking about the questions, I will just take the opportunity to really show you the websites that we of Comrade, the Crypt Network website, our GitHub repos. So it's still relatively early days for all the projects, but you can, yeah, please start repos and check out for updates. And also, if you want to dig more about the blockchain aspects, join our Apache Discord channel here.
All right, Branimir. Thanks a lot. I think that I would ask one last question before we go. So, like in that your system, it's obvious that you have a lot of events and streaming events being moved from one part to another. Do you enforce any exactly once processing guarantee? So imagine that the following happens: one of the function pods starts processing an event, but then it fails in the middle, and it does not acknowledge this event processing to your cluster storage. So how do you handle these scenarios? Because I do believe that it's quite important for the use cases like the blockchain one you just described.
Yeah, that's true. So for the blockchain itself, there are two aspects of this question. So the first one is more like the Ignite aspect of the question, like more like the Perper aspect of the question. So here on this level, we guarantee at least one. So not exactly one.
Okay.
However, on the blockchain aspect is a bit easier because the actual computation here, it's abstracted from the, so what we're running here is really abstracted, like abstracted computation. So we are doing so we are doing basically those state machines, and the critical aspect, so the critical part of those state machines where we have to guarantee determinism and exactly once, it's basically a very small portion of the actual system, which is the validation of the actual agent. So what we do here is that if there is a certain cluster failure or machine failure, what we do is just we discard and re-evaluate again the agent. So it's kind of something that you can do on application layer. But so this is kind of the approach that we are following.
All right. Thanks. It's clear to me right now. So I don't have any questions. Thanks a lot. As I said before, that was a wonderful presentation in terms of the way how you found like how you can utilize different technologies together. Azure Functions, Ignite, streaming, like, and eventually for the blockchain. Great to know, and thanks for presenting to us. Hope to see you in the future, and we wish you good luck with your project and with your customers.
And we are waiting for your feedback in our discussion about next version of Apache Ignite.
Okay, thank you so much. Well, thank you for the wonderful work that you're putting in this project. It's really a wonderful piece of technology, and it really opened a lot of opportunities for us.
I think that we can share some news on what's coming in our group. So the next topic would be by the Ignite PMC chair, and he is going to give he's going to run an unusual conversation on when you should not use Apache Ignite. So in many use cases, in many scenarios, you can hear us presenting how Ignite is good, how Ignite is great, and how we use it our projects. But Dmitry, the PMC chair, decided to take another view on when you should not use Ignite. What are not the best use cases of Ignite? So that one is coming. So watch our group announcements. It will be scheduled soon. And the other one that we already mentioned is the discussion about Ignite 3.0 release. The release manager, another Ignite PMC member and committer is going to explain you in details what's coming. And also that will be the opportunity to share your feedback on what have to be added personally. So like watch our group announcements. Everything is coming like in August and September. In September, right, Ksenia? Yes.
Yes, in September. Dmitry's meetup will be on September 8th. And we will very soon announce the discussion about the next version of Ignite. It will also be in September.
Thanks a lot. Thanks a lot, Branimir, and thanks everybody for staying.
Have a good evening, good night, or good day.